And hello, everyone. This is the first of two anticipated lectures on igneous rocks. I've got about 20 slides that I'm planning on going through today, and then I'm going to stop short of magma generation because I want us kind of fresh and ready for that. It's not difficult, but there's some tricky things, and I want to honestly think a little bit more about how I'm going to teach it. So today we'll begin with just talking about igneous rocks in general. And then the next lecture will be on magma generation and intrusive activity and things like that. So should divide up pretty nicely. Probably going to be two relatively short lectures as opposed to one kind of long one. And I'm once again not filming myself because I'm pretty sure there's some stuff in the lower right hand corner that I'd rather you see than me. So igneous rocks are rocks that form from molten rock, from either magma or lava. And so we want to kind of, first of all, take a little bit of a look at that because, we say molten rock, not, and I'm trying to get my slide to go, there we go. And, we say molten rock. Not liquid rock because it's not actually liquid. It's sort of almost the consistency of a milkshake, if you will. And actually, when we think about magma or lava, magma if it's below ground, lava if it's above ground. We'll talk more about that when we talk about volcanoes. But there's three components to it, right? There is a liquid component to it. There is actually a liquid component made usually of silicon and oxygen. That's the stuff that has the lowest melting temperature, and so will usually be the actual liquid. Now, don't think water, right? Now, water. I mean, there might be a little water in there, but really, probably not. Especially in the case of lava, right? Because without the pressure, that water is going to just boil right away. So there is some liquid, but then there are also some solid. There'll be some solid silicate minerals, usually some things like olivine and pyroxene. And what minerals you have there are going to vary with the temperature of the magma or the lava. And then, of course, right after I said no water, my third bullet point says water, and that's going to be for magma, not lava. Okay, so as long as the molten rock is under pressure, there will be some water content actually, yeah. So you have volatiles, right? Water, carbon dioxide, sulfur dioxide, a number of things. And then, when we get to volcanoes, we're going to see how, those volatiles really do come into play when we start thinking about, how explosive is that volcano going to be? Well, what volatiles are you dealing with, right? And so it's pretty simple. When we think about magma or lava, we think about liquid, solid, and then volatiles, which are in a lot of cases gas. So it sort of matches up well with the three common states of matter that we're used to dealing with. So as this lava or magma cools, that's where igneous rocks come from, right? They come from that cooled lava or magma. So this is sort of the central slide, if you will, for igneous rocks, right? So we see an igneous rock, and we want a couple things. First of all, we want to know how it got there, what's going on. We want to use it to interpret the environment, but then we also would like to give it a name. We'd like to classify it. So when we think about igneous rocks, there are two things that we worry about: composition and texture. Composition and texture. And no matter how far you go in igneous rocks or in geology, it always comes back to composition and texture. I remember when I was at Florida State taking igneous petrology, a whole course in nothing but igneous rocks. Excuse me while I take a drink of water here. A whole course in nothing but igneous rocks. And you'll have to understand, I'm a paleontologist. I don't care that much about igneous rocks, right? There, with the exception of some volcanic ash, there really aren't fossils in igneous rock. So my interest in igneous rock is really pretty low. But as a geology major, I had to take a whole class in nothing but igneous rocks. And I'm sitting in the lab, and I don't know, I must have looked pretty pitiful because the TA came in and she said, "What's wrong?" And I said, "I'm just never going to keep these straight. I mean, I've got 250 igneous rocks rolling around in my head, and I'm never going to keep them all straight." And she says, "Okay." She says, "What did you learn about igneous rocks in, Geology 101?" And I said, "Composition and texture. Composition, texture." She's like, "Yep," and that's still what it is. And so now we're not going to have anywhere near 250 igneous rocks. We're going to have, I don't know, 10 or so. Okay, if you're in lab, if you're in class, we just need to learn about them. So, but it really does always come back to composition and texture. So what do we mean by composition? Well, when we track composition in igneous rocks, what we're really talking about are those two most common elements, silicon, Si, and oxygen, O, in the Earth's crust. Now remember from our mineral lecture that that silicon and oxygen make that silicon oxygen tetrahedron, and they make the silicate minerals, which recall that we also called the rock forming minerals, right? And so when we look at igneous rocks, most of the minerals that we're looking at are silicate minerals. In fact, all of the minerals that you're looking at are silicate minerals of one kind or another. Now, these silicate minerals can have varying amounts of silica in them. The ones higher up there, the things like olivine and pyroxene, they don't have as much silica as does, for example, feldspar or quartz, which is pure silica. Okay, so when we think about composition, we have three different categories. We have mafic rocks with very little silica. We have intermediate rocks that have a little bit more silica, and then we have felsic rocks that are a whole bunch of silica. Now understand that even mafic rocks, this is relative, right? Mafic rocks might have 60% silica. Okay, it's just that felsic rocks have 95% silica to 98% silica. So don't worry about the numbers, just worry about the relative abundances, right? So mafic don't have a lot of silica. Intermediates have more silica, and felsic have even more silica. Okay, and so if we look over here, I've got a granite up here, and I've got a gabbro down here. This is what a rock with a lot of silica looks like. Okay, it's generally lighter in color. Now, granite's a little bit tricky because if that feldspar is pink, it darkens the rock overall. So you have to be a wee bit careful with granites, but generally lighter in color. And then mafic rocks like this gabbro down here are always dark in color. They just are. So when we think about composition in igneous rocks, now I know that in the mineral lecture I harped on don't use color, don't use color, don't use color. Here we can, in a sense, use color, but not in the sense of, what is it, pink or white, but just darker versus lighter. Okay, mafic igneous rocks like this gabbro down here are darker in color. Felsic igneous rocks are lighter in color, and intermediates are going to be somewhere in between. I'll show you that here in just a minute. So the other thing that we worry about is texture. Now, if you had me for earth science, all we really did for texture was coarse grained and fine grained. In this class, the fine grained is aphonetic, and the coarse grained is phaneritic. Okay, so we have some fancier words than we did in earth science, if you were with me for earth science, but the concepts are the same. And then there's a few more textures that we want to worry about too. Okay, so texture refers to the size of the crystals in the rock, and in its simplest, you just literally pick the rock up and look at it. Okay, can you see nice big individual honkin' mineral grains the way you do in this granite pretty easily, or not? Okay, now the fun thing about texture is it's related to cooling speed. The slower the rock cools, the larger the mineral grains are going to be. And so, this is kind of the difference between making ice in your freezer, where you freeze it pretty quickly, and making a snowflake in the atmosphere, where it happens a lot more slowly and you get a nice pretty crystal. Okay, so igneous rocks that cool slowly tend to make larger crystals, whereas igneous rocks that cool quickly make smaller crystals. I'll show you here in a minute. Just bear with me. So we can relate these textures to the cooling speed of the rock. So these are not in the best order in the world. So just bear with me. So if a rock cools slowly, now where does this slow cooling happen? Well, this slow cooling happens underground. Right? So if the rock is cooling slowly underground, so we got a hypothetical volcano here, but you need not have a volcano. You could just have a body of magma underneath there, cooling slowly. Okay, so that underground setting produces slow cooling, which produces visible crystals and therefore a phaneritic igneous rock. That's what we call that. This granite is phaneritic. So is that gabbro. It's just not as obvious. But when you look at the rock and you pick it up, and it just has visible interlocking crystals, okay, that is a phaneritic igneous rock. And so, without knowing anything at all, if you pick up, an igneous rock, you can tell where it cooled. You can tell if it cooled underground or if it cooled on the surface. Because if it cooled on the surface, it's going to cool faster. And that's going to produce smaller crystals. And by smaller crystals, I mean crystals that you can't see with the naked eye. The rock is just going to look like mush igneous rock. Okay, we call that texture aphanetic, and I'll show you some more of them. But for now, you can see this basalt down here in the lower right from this lava flow. That's going to produce aphanetic texture, so we know that it cooled above ground, right? So once again, without really knowing anything, okay, other than that, you can pick up an igneous rock and tell someone where it cooled. Did it cool above ground or did it cool below ground? Well, if you can see crystals, it cooled below ground. On the other hand, if you can't make out any crystals, it cooled above ground. And then, if it cools really fast, you get glassy texture, right? And if we look back here, you can see this piece of obsidian here, okay? Glassy. Now, if phaneritic rocks cool slowly and aphanetic rocks cool quickly, went too far, sorry. Glassy rocks cool very quickly. Now, with glassy textures, rocks like obsidian, now rather than just letting the rock cool, it's been quenched. The lava flow went into some water, or there was some rain, or a snowbank, or something like that. Okay, so here we're just leaving it alone and letting it cool underground. Here, we're just leaving it alone and letting it cool above ground. Here, it's getting hosed down with water or snow or flowing into the ocean or something like that, right? This is cooling in minutes, okay? This is cooling in years, if you want to attach some sort of numbers to them, although that's really kind of tricky to do. Anyway, so there's kind of those three, phaneritic, aphanetic, and then glassy. Porphyritic is interesting. What happens if you're hanging out underground, maybe under a volcano, and you're cooling slowly, but then the volcano erupts, right? So what you're going to get then is you're going to get a rock with pretty big crystals in it from that slow cooling, and you can see me pointing to one right there, and then you can see the white crystals in this porphyritic rock, formed when the rock was cooling slowly underground. But then it erupted, right? The volcano erupted, and now suddenly it's cooling quickly. And so you get this what we call ground mass, but this aphanetic rock around those crystals. So with porphyritic rocks, don't think pore like a hole, that's going to be vesicular. We'll talk about that in a minute, okay? Think more just porphyritic doesn't mean a hole. It just means that there's some really big crystals and then some aphonetic ground mass around those crystals, because you had two different cooling speeds, right? You had an initial slow cooling that will make these large crystals, and then an eruptive event that put this magma, now lava, on the ground surface, and so now you switch, and now you have fast cooling. So you're going to have two different cooling speeds that correspond with two different settings, and so vesicular is something that people confuse with porphyritic a lot, because vesicular has holes in it, and so people think pore. No. They're called vesicles. Okay, and so you can see this piece of pumice here, right? This happens when you have a lot of volatiles, a lot of gases under pressure, and then when they reach the surface, they escape. They make holes in the rock, these little bubbles in the rock that are preserved as the rock cools. So you kind of got aphonetic rock around it, obviously, but you got these holes. Pumice is one very, very common vesicular rock, and you might have some of that in your bathroom for scrubbing calluses or something like that. I don't know what y'all do with the rock in the bathroom. That's between you and the rock, but yeah, it's a very, very common rock. And then finally, a lot of times we get pyroclastic rocks, which is volcanic ash, right? So if we go back to our picture here. You'll get a lot of ash thrown up in the air, and then it comes down, and it's got a particular texture. It varies with if it was hot when it came down or cold when it came down, and what happened afterwards. But with some experience, you can start to recognize volcanic ashes when you see them. And so those are the compositions and textures that we deal with. Let's take a little bit closer look at them, though, just so we're sure we get this. So composition is, remember, the amount of silica that you have, right? And so I chose a granite over here, because a white granite, because that gives us really the idea that these are lighter in color, right? And so more silica, something like a granite, a little bit less silica, intermediate in composition, that would be something like a diorite, and then mafic would be something like a gabbro. Okay, but notice what I want you to focus on here is the color difference. Okay, or just, I don't know, is it actually color? The difference between lighter, intermediate, and darker. Okay, that's our key to composition of igneous rocks. Okay, now just as a I don't know, as something to think about when you're in the field, you really want to make sure you're looking at a fresh surface, because you could crack open something that doesn't look much like a granite on the outside, and suddenly it does on the inside. And I've got a little virtual field trip I might throw up for you guys to have a look at that shows that. But anyway, if we're looking at fresh rock, we've got more silica, lighter color, less silica, a little bit darker in color, and then dark in color, even less silica, right? So that's kind of what composition looks like, right? Texture looks like this, right? I've got fast cooling obsidian here, and then intermediate cooling rhyolite here, and then slow cooling granite here, right? And remember that this is all about the cooling speed and the location, right? This slow cooling happens underground, so this granite cooled underground. So once again, without really knowing anything about the rock, you know where it cooled: underground. Okay, rhyolite cooled above ground, and then obsidian cooled very quickly above ground, but also quenched, right? So this has crystals that are visible to the naked eye. This does not. But if I took out just a 10-powered hand lens and put it on that rhyolite, you'd be able to see some crystals, okay? Don't be confused if you can look at the rock and go, oh, well, look, there's a little, I don't know if that's a crystal or a hole, but, there's a little crystal, and there's a little crystal. No. Right, that those don't count. Okay, what we're talking about here is rock that is made entirely of interlocking crystals, and then so if these are visible with the naked eye, These are visible with a hand lens. These are no. It's not that they're not visible; they're not there. You need like an X-ray diffractometer or something weird like that to get any kind of crystallography out of this. And so just to the naked eye, interlocking crystals, no crystals, visible crystals, and not only no crystals but very smooth, and there's just no crystals at all, really. Just to pick up a couple of the other some better pictures of a couple of the other rocks. I think this is just a bigger picture of the one we looked at before, and so is this. But that's okay. This is a porphyritic rock, an andesite porphyry, and you can see nice big honking crystals surrounded by aphenetic ground mass. That tells us there were two different cooling regimes here, right? A slow one followed by a fast one. Here's that same piece of pumice from before, just bigger, and you can see all the vesicles in it, that vesicular texture. Pumice is kind of unique in that a lot of it floats. Not all of it. Pumice has a density of right at 1 because of all the air in it, and so you put it into water, and if it's 0.95, it'll float. If it's 1.1, it'll sink. And in my experience, it's about half and half. But a lot of it does float. A lot of it does. And so this one in particular, this one's floating pretty well, actually. So it's the only rock that I know of that you can just pick it up and throw it into water, and it floats. It's kind of fun that way. Vesicular texture, though, and in this case, it is that lighter color tells us that it's felsic. And then our volcanic textures. We could go on about these, but I'm really not going to. But when you have volcanic texture, a lot of times that rock is called a tuff. If the fragments were kind of melty and soft when they came together, that might be a welded tuff. If you have a lot of fragments of rock that were thrown in the air by the volcano, that gets called a volcanic breccia. And now we're really kind of dealing with the intersection of igneous and sedimentary rocks, which we'll talk about more when we talk about sedimentary rocks. So identifying these is a question of asking yourself, what is its composition and what is its texture, right? If the rock is felsic, for example, and this is a scan, by the way, from the lab manual, and I'm not honestly crazy about this drawing, and I might even go back and do another one, because it's not terribly clear, and you've got all these different minerals doing weird things in here, and it's a wee bit, I don't know. I find it. I mean, I can understand it, but if I'm you guys looking at it, I'm like, what the heck is all that? Yeah, don't concentrate too much on this. Okay, if it's lighter in color, it's felsic. Oops. Oh. Sorry, guys. Let me go back. Here we go. If it's lighter in color, it's felsic. If it's felsic, it's either granite or rhyolite. Both of those are light in color, right? And we can see up here, here's some granite over here, and here's some rhyolite over here. Also a scan from the lab manual. Now the granite has some of that pink feldspar in it, so it might look a wee bit darker than maybe it should. But so coarse grained here, fine grained here, right? So if it's felsic and it's coarse grained, it's granite. If it's felsic and fine grained, it's rhyolite. And I just made the decision to show you guys something. In fact, I'm gonna pause this video and do something else real quick, because I'll explain this, but then I'm going to show you a simplified version of it. So give me just a second here, and for you guys, I will be right back. Okay, I'm back, and I've put something together for us on the next slide that I think will help a lot. So anyway, as we think about this, if something is felsic, if a rock is felsic, it could either be granite or rhyolite, depending on its texture. If it's phaneritic, it's granite. If it's aphenetic, it's rhyolite. If something is intermediate in composition, it could either be diorite or andesite. Don't worry too much about the minerals in here. It could either be diorite or andesite. If it is phaneritic, in other words, intrusive, cooled underground, then it's diorite. If it is aphanetic, cooled above ground, it's andesite. And I know that this is a wee bit confusing because there's these tiny little crystalline things here, but it's not made of big interlocking crystals, right? And so this is frequently what andesite looks like, and it can be a wee bit confusing. And then if it's mafic in composition, it's either basalt or gabbro, right? If it's coarse grain or phaneritic, cooled underground, therefore we call it intrusive, it's going to be gabbro. And then if it cooled above ground quickly and is aphanetic, it's basalt. Gabbro can be a little bit tricky because all the minerals are dark. They just are. And so you look at it and you think that you're looking at something that's just a pile of aphanetic rock or something, but then if you look a little bit closer, you see their crystals, which is why they make a point of pointing out these cleavage flashes here, where the cleavage on these mafic minerals is reflecting light, which tells you, yeah, wait a second, yeah, there's big crystals there. The problem is all the crystals kind of look the same. And then they bring up the ultramafic rocks over here, which are even more mafic than mafic. They have very little, sometimes no quartz in them at all. And the big one there that we deal with is a rock named peridotite, and there it is. And so let me just check on something really quick here. Sorry, I hit the space bar and something weird happened, and I just wanted to make sure I wasn't talking and not recording. So, peridotite is an interesting rock. It looks like that. It's ultramafic, and it came from the mantle of the Earth. So this is what, if the mantle of the Earth were to come up to the surface, this is what it looks like. It's a fascinating rock, really. So this works. Okay, let me show you the grid that I use, and if you're in the lab, I'm going to make this available to you. This might look worse, but it's actually better. And so across the top here, we've got composition, mafic if it's dark in color, intermediate if it's intermediate in color, and felsic if it's lighter in color. And then I've got down here, what I call the big six, right? Basalt, gabbro, andesite, diorite, rhyolite, and granite, right? And so basalt and gabbro are both mafic, but basalt is aphanetic, no visible crystals. Gabbro is phaneritic, visible crystals, right? All these phaneritic rocks cool underground, which is why I kind of visually put them on the bottom, okay? Which may or may not help, but there it is, okay? Intermediate is either andesite or diorite, if we're thinking about these six on the bottom. Andesite cools above ground, diorite cools below ground. And then if it's felsic, it's either granite or rhyolite. Granite if it cooled below ground, and is phaneritic. Rhyolite if it cooled above ground. Okay, obsidian doesn't have a composition. I know a lot of it is dark in color. Doesn't matter. Doesn't have composition. We don't worry about composition. If you pick up an igneous rock and it's glassy in texture, it's obsidian. Don't go any further. Don't worry about composition. Okay, and then our two vesicular textures, pumice we've already seen, and then if it's felsic, it's going to be light in color, and then scoria, which we haven't seen yet, but I'm about to show you, if it's mafic and dark in color. And then over here, I put porphyry with its porphyritic texture, 2 crystal sizes, because it kind of spans from, it kind of spans the different the different textures. And so let's add some pictures. Okay, so first of all, I found a much better picture of a porphyry. Isn't that pretty? Those really big crystals and all that ground mass, right? So 2 different cooling speeds. Okay, and then over here we have a piece of obsidian, the same piece we've kind of been looking at. Glassy texture. Do not worry about its composition because you can't. Okay, you don't know. for the two vesicular rocks, I tried to put them up here, but they didn't really fit, so I just put them down here. Here's the piece of pumice that you've been looking at, and then here's a piece of scoria. Which is, sort of the mafic version of that. Right now, scoria is not going to float. I actually cropped off the top of it. Sorry, scoria is not going to float. You throw it in the water, it's just going to sink. But you can definitely see that vesicular texture, where you had volatiles and making air bubbles as they as the rock flowed over the surface, and those air bubbles were preserved, right? And then I took the picture that we were using for basalt, gabbro, andesite, diorite, rhyolite, granite. I flipped it and put it down here. So granite here, diorite here, gabbro here, and then the the aphonetic companion to granite is rhyolite. The aphonetic companion to diorite is andesite, and the aphonetic companion to gabbro is basalt. Right, so I've got them. I had to mirror image flip it, but I've got these arranged like this, and this arranged like that. Okay, like that. Okay. So there's igneous rocks in a very small nutshell. Like I said, if you want to be a geologist when you grow up, you're going to take a whole class in nothing but igneous rocks, and so you'll go much deeper then. But let's take a look at some in the field, right? And so if we want to see mafic igneous rocks, Hawaii is, of course, one good and maybe obvious place to go. You get a lot of really spectacular volcanic eruptions and a lot of lava flows. I should update this from that eruption a couple years ago in the summertime. But yeah, but another place maybe you don't know about is the Deccan Traps in India. This is a huge lava flow. Here's a picture of India, and then here's the Deccan Traps, right? I mean, this is a considerable portion of the entire country of India. It is absolutely huge, and it's not just one lava flow. It's a bunch of them stacked on top of each other, which makes it even more interesting, really. And then what makes it really interesting is this lava flow, this volcanic event, happened about the same time the dinosaurs were going extinct. Or let's say the non-avian dinosaurs were going extinct. Which is kind of interesting. Now, I mean, extinctions, and we'll probably talk about this a little bit later on, but the paleontologist in me is compelled to tell you right now that, extinctions are probably a lot more complicated than you think they are. It's never as simple as some big asteroid smacked into the Earth and killed everything. It really didn't work that way. Yes, an asteroid hit the Earth. We know that. But beyond that, the effects, and it's kind of interesting. And so, we're beginning to think more in terms of a combination of events now. And when we think about the dinosaur extinction or the non-avian dinosaur extinction, let's just call it the KT extinction, this definitely comes into play. Because along with all this lava, there's going to be gas and all kinds of stuff spewed up into the air. But this is mafic. Here, let me go back and show you the rock. This is mafic igneous rock, and it goes on and on and on, and there are literally hundreds of lava flows stacked up on top of each other here. We don't need to go all the way to India to see that, though. We can go to Washington and Oregon. And see the Columbia River basalts. Here, I'll show you a map again. So, this look at all this green. Columbia River basalts. Considerably younger than the Deccan Traps, but you can see how extensive they are, and here's what they look like. This feature that you see with this linear deal here, where they end up looking like columns, is a natural thing called columnar jointing that you frequently see in mafic lava flows. Under the right conditions, the lava will contract as it cools and pop into these hexagonal columns. People look at this a lot of times and think that it must be somehow made by people or whatnot. It's not. It is a perfectly natural thing, and I'll show you another example of it here in just a second. And so once again, if you want to see that Columbia River basalts up here, Washington, Oregon, and then I see here actually over into Idaho a little bit too. So really, really beautiful up there. And here's some from Texas. Some nice basalt. You can see this kind of ropey texture that it has here. That's got a Hawaiian word. It's called pahoihoi. When you see that ropey texture, we'll talk more about pahoihoi when we talk about volcanoes. But you head out west, and it doesn't take much to find a lava flow. There's quite a few of them out there. Or you can go to Ireland, a place called the Giant's Causeway. This is more of that columnar jointing you see here. This is a World Heritage Site. First of all, it's a beautiful place, but it's also unique in that you got this lava flow with this columnar jointing, and there are other places where you can look at it more from the side and get more of a better look at it. But the legend here is that there was a giant who lived in Ireland, and his girlfriend lived over in England, and so he built a road into the sea so that he could go walk on it and visit his girlfriend. It's all terribly romantic, but it's also natural, right? This wasn't made by a giant or anything other than nature with a lava flow and then contraction of that lava into these hexagonal joints. If we want to see intermediate igneous rocks, we need to probably find some volcanoes. And in particular, the volcanoes of our Cascade Range. This is Mount St. Helens. And so what you're doing here, and we talked about this when we talked about plate tectonics, you've got this ocean-continent convergent boundary. Now I can kind of use some words, and I should probably throw up a picture here, but I'm not going to. Now I can use some new words, right? You've got that oceanic crust that is mafic in composition as it slides underneath the continental crust. The continental crust is felsic in composition. The mafic rock melts, works its way up through the continental rock. Those mix, and then in the end, what you end up with on the top is an intermediate composition volcano. And as we will see when we do talk about volcanoes, those are the violent ones. Those are the ones that you really kind of want to avoid. Those intermediate volcanoes of the Cascade Range are not the happy little Hawaiian, go roast a pig on the beach, have a luau volcanoes. Those are, runaway or die volcanoes. And when we talk about volcanoes, we'll talk more about that. Felsic igneous rocks are a bit easier to find. First of all, seems like everyone these days has granite countertops, and okay, yeah, that's felsic igneous rock. If we want to see it in the wild, though, let's go to I sorry about that, everyone. Let's go forward. There we go, and there we go. If we want to see felsic igneous rocks, you'll find some granite in the wild. This is Stone Mountain. I was down there just a couple weeks ago. It is a big old honking piece of granite sticking up out of the ground. They carved, 3 treasonous rednecks onto the face of it. Jeb Stuart and Jefferson Davis and I think Stonewall Jackson. 3 treasonous rednecks. Anyway, but it is geologically fascinating because it is a big old honking piece of granite sticking out of the ground. Now wait a second, because granite is phaneritic. It's coarse grained, therefore it cooled underground. Right. Same thing here. Right. Let's look at Yosemite. Big old honking piece of granite sticking out of the ground. And what's more, all the rock that you see in this picture is granite. All of it. So wait a second though, because once again it cooled underground. But yet it is not underground now, not by a long shot, right? And this is the trick here, right? Once again, the fact that it's a granite, yay, you gave it a name, but that doesn't mean, that's not an interpretation of what actually happened out there. And so, in the case of these granites exposed above ground, we know that what we're dealing with here is a lot of erosion. Right. If I go back, I know a little bit more about the Stone Mountain granite, so let me go back to that. This is about 300 million years old. So this rock cooled 300 million years ago. Okay, when Pangea came together, the heat and the pressure deep down melted some rock, made a magma chamber that probably rose a bit but never breached the ground surface. And then 300 million years ago, it cooled slowly below ground. Now, once it cools, it's not going anywhere. I mean, once it cools, it's there. Okay, and so what happens then? Well, we just threw up the Appalachian Mountains off to the west, and so you're going to have a lot of erosion coming down out of those mountains, and you're going to erode the ground surface down to, in this case, several hundred feet lower than the top of the granite body. Now, the thing about the Stone Mountain granite is this is really the tip of the granite iceberg. There's a lot more of it below ground. And if you've ever been there, you know that you're seeing Stone Mountain granite way before you get to this big old chunk of it sticking out of the ground here. So it is really, like I say, the tip of the granite iceberg, but it is exposed because of erosion, right? Yellowstone is going to be the same way. I just don't know that story as well. I need to learn it, but still, anytime you see exposed granite like that, you know that there was an event that caused rock to melt underground, and then subsequent erosion will bring that rock up to the surface. And so, and it seems like there was something else I wanted to say, and I do not remember what it was. Okay. I know what I want to say. Let me go back to Stone Mountain real quick. This rock was quarried along the backside. That footage that I show you during our break time of the grist mill is right next to a quarry. The Stone Mountain granite was quarried, and there were contracts with the federal government to quarry the Stone Mountain granite for building stone. And there are buildings in Pinellas County. The Bay Pines VA Center and a few post offices are built of Stone Mountain granite. As you go, looking around and looking at buildings and stuff, because I know we all do this, right? We all go looking at building stones from a geological point of view, or maybe you do now. But there are a couple of post offices and the Bay Pines VA Center. Some buildings are made from the Stone Mountain granite. And then if you go to Atlanta, there's a lot of Stone Mountain granite, an awful lot of it. It is very frequently a building stone. Speaking of building stones, here's another granite. This is the Llano granite in Texas, Llano, which in Spanish would be pronounced Llano, with my horrible Spanish accent, which I don't even have. But the Llano granite is along the Llano River in a region of Texas called the Llano Estacado, near the town of Llano. There's a lot of Llanos going on here, but it is a distinctly pink granite. There are some really nice, pretty pink feldspar crystals that stick out of this granite. I've worked around here. Oddly enough, I wasn't working on the granite. I was working on the insects in the river for another project, or non-geological project. But when it came time for Texas to build a state capital, they wanted a rock from Texas because Texas. And so, of course, the capital of Texas is Austin, and Austin sits right in the middle of a beautiful white limestone, called the Austin Chalk. And if you go to Austin, you will see a lot of buildings made out of the Austin Chalk. And so people suggested, well, let's build the Capitol building out of the Austin Chalk. It's right here. It's pretty. It's blindingly white in big buildings. And it'll make a really pretty Capitol building. But for some reason, they said, no, we don't want to do that. We want something else. And so someone said, well, there's always the Llano granite. We could go quarry the Llano granite to build our capital. And they said, yes, let's do that. And so Texas has built a distinctly pink Capitol building. This picture does not even do it justice. It is pink. When you look at it at the end of Congress Street there in Austin, it sparkles because it's phaneritic. It's got these big pink sparkly crystals, which it's an impressive building, but it's just, I don't know, I just kind of find it funny that it's pink. Next time, we're going to talk about generating magma, but I'd like us, me in particular, maybe, to be a little bit fresh for that. So I'm going to, my timer tells me that I'm about 45 minutes into this lecture, and I think that's probably a good time to stop. And then next time when we come back on, well, in this case, depending on when you're listening to this, my plan is Friday, but I don't know, semesters later it might be different. But anyway, next time we do this, I'll be talking about generating magma. So, okay, y'all take care, and I will get this compiled and get it up for you. Everyone take care. Bye-bye.